Okay, so the plan for today is to start on the definite integral section 5.2 and we'll complete 5.2 and get started on 5.3, the fundamental theorem of calculus. Um, Obviously, by the title of it, you can probably tell that it's an important section. So we'll start 5.3 today, likely finish 5.3 next class, and continue on with chapter 5. The we have two quotes of the day for today in honor of Veterans Day. Uh, so happy, or I guess not happy Veterans Day, but whatever. We appreciate our veterans. If any of you folks are veterans, that's what the quotes of the day today relate to. This is a kind of it's a hard quote to track down, but the best I can find is that it's from some guy, Richard Grenier, summarizing some ideas from Orwell, possibly from Kipling, but I kind of like his phrasing of this quote better than their ideas. Um, but the quote is that we live in relative peace and comfort only because of rough men who stand ready, willing to do violence in our behalf. So the fact that we're able to sit in our nice, heated and air-conditioned homes and do things like zoom into math class, we're able to do that because there are folks who have made a lot of sacrifices on our behalves. And, uh, that's certainly not true for everybody around the world right now. And that's not true for, uh, even the US historically. So uh, we are, I think, in this light anyway, pretty fortunate. And this second quote is kind of an excerpt from a letter that John Adams wrote. So the whole thing is kind of long, so I've kind of shortened it here, but I think kept the spirit of the quote. And he's discussing, I forget who he was writing this letter to, but he was discussing his duty to study government. Um, and he says, I must study politics and war so that our sons may study mathematics and philosophy, commerce and agriculture, in order to give their children a right to study painting, poetry, and music. So kind of roughly speaking, you have to sort out the physical violence first to establish security. You have to then sort out the logical side of things, the kind of building up of an economy and resources and so on, so that we can establish a society that functions well and has surpluses. And once we have sufficient surplus, we then have the freedom to study painting, poetry, music, etc., things that maybe in some sense don't directly contribute to absolute life necessities, but are, kind of in a sense, and if you've ever seen Robin Williams in Dead Poets Society, kind of like the reason that we live, so to speak, right? So I think most of us are kind of in the middle hierarchy here as far as our career goals and our what we view as maybe our eventual place in society, doing something mathematical or technical, something with physics or chemistry or engineering, something like that, like building the structure of society. But that's not to say that the folks who are down the hall, I guess metaphorically speaking, in a Zoom meeting, but who are studying painting and poetry are any less valuable. And I probably would make an argument that philosophy really belongs in kind of in all three of these hierarchies, all three levels of this hierarchy, but that's a bit of a tangential point. Um, we kind of need to study philosophy in order to be able to study politics and war and so on. But anyway, so our thanks to, or my thanks anyway, to the folks who have given us the right or the ability to move up these levels and have nice, safe environment to engage in what we're going to engage in a few minutes here. So even though math might not be the most interesting thing in the world, it's certainly a privilege for us to be able to sit here and talk about definite integrals as opposed to, you know, uh, war and so on. Okay, so last time just to kind of quickly recap last time, I suppose, because we really shifted gears, we wrapped up the idea of derivatives, which was the main focus, well, essentially the only focus of chapters 3 and 4, and which was what the end of chapter 2 led into. And we kind of, wrapped that up and put a bow on it. And like I mentioned last time, we have historically added a bit more into Calc 3 over the decades, and that's pushed a little bit into Calc 2 and pushed a little bit of Calc 2 into Calc 1. So we have um, the boundaries between the different calculus courses are a little fuzzier these days than maybe they used to be. So we've wrapped up differentiation and we're moving into integration. And in 5.1, we looked at the area problem, as we called it. And we said our goal was to do something like find the area under a curve or find the signed area between a curve given by a function, the x-axis, and two lines, x equals a and x equals b. Uh, and we saw that if we have a straight line, if our function makes a straight line, that's pretty easy to do with geometry. But if our function makes a curved line, kind of at best, just jumping down here a little bit, at best, if we look at something like this, a pretty straightforward function, I mean, just a power function essentially, it was a heck of a lot of work to argue uh, what the value of this area was, what the value of this integral was. I'm jumping ahead. We haven't introduced this notation quite yet, um, but we looked at the area under 4x cubed from 0 to 4 and saw that it was 256. And we kind of we took a slightly different approach than how the definite integral is going to be defined, but we were able to argue for that area in a way that's pretty similar to how we're going to define the definite integral in just a minute here. So that is introducing the new idea. If you remember at the beginning of chapter 3, or actually, I suppose it was the beginning of chapter 2, right? The tangent and velocity problems to kind of kick off the beginning of the course. Those were the motivating problems for building up limits to the point where we could get to derivatives and work through chapters 3 and 4. So the area problem is our motivating problem for building up this idea of integrals, which is the focus of chapter 5 and the focus of much of calculus 2, again, and kind of until you get to the very end, which is where it bleeds into calculus 3 a little bit. So this is kind of a preview, I suppose, a prologue to calculus 2. And when you get into calculus 2, when you take that, next semester or whenever you plan to take it, we'll pretty much do like a quick review of chapter 5, some of this important material, and then just continue on from there through Stewart. That is, if you take it with me, different faculty teach things a little bit differently, but this material, is in Calc 1 for everybody. So that is kind of where we left off last time. And we investigated this function 4x cubed, found the area under it between 0 and 4. That involved setting up a sum, kind of getting that sum into a simpler form where we didn't have n terms being added up, but we had just a function of n that we could evaluate. And then taking a limit, that gave us an upper bound. And then as an exercise, I said, you could do the lower bound, and then we basically use squeeze theorem and argue that that is the value for that area. That was section 5.1. So now let's try to formalize that a little bit in 5.2, the definite integral. So definition, the integral of f from a to b, or sometimes we call it the definite integral of f from a to b, but here the context is clear. The integral of f from a to b is denoted this way. So first, the notation. This is this little squiggle kind of guy here. It's kind of like an S, but just elongated. So it's kind of like a tall S like that. I think it might refer to some like our sigma here. The summation symbol is the Greek capital letter S, the Greek capital sigma. So I've heard that before. I mean, it looks a little bit like an S to me. I've heard that before. It seems fairly reputable, but I don't know 100% that that's true. But we saw that if we're looking for areas under curves, we kind of chop the area into a bunch of little boxes. We add up the areas of the boxes, and that's a sum. So this integral is kind of like a summation. We have a kind of a subscript and a superscript that look like that. sometimes they look like this here whenever the font is working nicely, and sometimes they work, or sometimes they look a little more like this, where they're kind of like squeezed in next to the integral symbol. The font is more like inline, you know, it's a little less pretty, but this subscript A and superscript B, they refer to the same thing, just slightly different looks to the notation. So just be aware of that. The notation looks a little bit different in different typefaces just because we're trying to squeeze a lot of information into a little bit of room, and you know, there's a little bit of ambiguity there. Okay, so this integral is defined as follows. It's the limit of this big sum. So let's break this down piece by piece. Excuse me. So let's suppose that I have some function f on an interval from a to b. And again, I'm looking for the signed area between this function and the x-axis. So there should be a positive area here. Now, last time what we did is we said, well, this is a curvy function. It's going to be hard to determine the area directly. But what I can do is I can chop my interval a to b into a bunch of subintervals. On each subinterval, I already have kind of three sides of a box. I have a flat left side, a flat right side, and a flat x-axis, a flat portion of the x-axis. The thing that's not flat on each of these boxes is the top here. So I have kind of a curvy top. But if my subinterval is pretty small, if it's a pretty narrow box, and if as long as f is kind of a reasonably nice function, then anywhere in here, I mean, the height of the function isn't going to deviate that much for a very small box. So I could take maybe the right endpoint and make my box height f at the right endpoint. Or maybe I would take the left endpoint and make my box height f of the left endpoint, or maybe even somewhere in the middle and take that as the height of the box. And when I do this for each of my different boxes here, ideally, we would think of these as being the same width, but it's just my inaccurate drawing that makes them look like they're not. So we do something like this here. We get a little bit of overestimate sometimes and a little bit of underestimation sometimes. But again, as the boxes get narrower and narrower and I get more and more of the boxes, these should fit these little, approximating the curvy function by essentially a piecewise constant function. It should fit better and better. Now, when I do this, I have subintervals of equal width, which is delta x, a little jump on the x-axis, which ends up being b minus a divided by n, where n is the number of boxes. So each little subinterval is 1/nth the width from a to b, b minus a over n. And the height is going to be something like f of x for some x that's in that interval, and we'll call that xi star. If this is the ith box, then xi star is going to be some index, some x value that we choose that's in that ith interval that's kind of indicated here. And we evaluate the function there to get the height of our box. And we see that the area of that box, maybe we call it a sub I, is going to be f of xi star times delta x. And that's going to be approximately the area between the function and the x-axis for the actual function over that little region. And then, of course, I have a bunch of these boxes, so I need to sum over the AIs. I equals 1 to n. There are n boxes. That's why I have this b minus a over n. So I need to sum this as well. So that's where all of this comes from, this inside here. We're taking each little subinterval. We have a box of base width delta x and of height f of xi star for some index xi that is, whoops, that is in that ith interval. That gives me the height, and the area of each little box is height times base width. And then I have to add up all those little areas of those little boxes. And if I didn't take a limit, if I just looked at this sum by itself, that would give me an approximation to the area under the function. We saw that with the 4x cubed function. We said, what about one box, two boxes, four boxes, and so on, and we can get a better and better approximation. Now, one thing to note is that for a standard function, for kind of an arbitrary function, when we break things up this way, we see that like sometimes we have a little bit of underestimation, sometimes a little overestimation. It's kind of unclear whether our estimate is an upper bound or a lower bound. We really set the 5.1 example up very specifically so that we could guarantee that if we do it this way, it's an upper bound, and that way it's a lower bound, and then apply the squeeze theorem. So we're not doing that here. We're not getting an upper bound and a lower bound and applying squeeze theorem. That was kind of an ad hoc approach for that section 5.1 problem. But what we're doing here is defining things a little more generally. So again, if I take the limit as n goes to infinity, as I have more and more boxes of that are skinnier and skinnier, of smaller and smaller base width, if that limit exists and is finite, then I say that that is the definite integral of f from a to b, that is the signed area under the curve on a to b, and I give it this this notation, integral a to b f of x dx. So a couple of notes. Well, let's start with the second note first. As I already mentioned, the definite integral gives the signed area between the function and the x-axis. Note that my function f in here, that's actually just f of xi. It's not like an absolute value or anything like that. If f were negative, then I would have a negative height times a base width, but the base width is always positive, right? B minus a over n is always a positive number. If the height is negative, height times base, negative times positive, gives me a negative output. So if my function is negative, if my curve is below the x-axis, the area it's going to return to me is a negative number. So I just have to realize that it's going to give me naturally the signed area between the function and the x-axis. If I don't want signed area, if I want absolute area, I might have to put absolute values on something or kind of break the problem into a couple of different pieces or something like that. I might have to think a little more deeply about it if I want an absolute area. So this naturally gives me the signed area between the function and the x-axis. The other note, which is very non-obvious, and there's a lot about this integral. This is called the Riemann integral. There's a lot about this integral that we're just really not going to touch in this class. That would be, something that would be dealt with in a real analysis class or a kind of an abstract theoretical calculus class that, if you were interested, you might take, say, after the calculus sequence. There's a lot about this that we're not going to discuss too much, but one thing that's very strange is that where you choose the xi star in each subinterval is completely immaterial, provided that the limit exists and is finite. If I choose all left endpoints, and I get an answer, I get a number out of here, I get, the area, the signed area under this function between a and b is 4. If I got that by choosing all the left endpoints, I'd get exactly the same result choosing all the right endpoints, or choosing all midpoints of the intervals. Or if I said on even I intervals, I choose the left endpoints, and on odd I intervals, I choose the right endpoints. Same thing, it doesn't matter. In fact, you could actually randomly choose in each interval. You could say, just pick some random x index in the first interval, get its output, some random x input in the second interval, get its output, and so on. It's completely immaterial where or how we choose the xi stars, as long as, of course, they satisfy the definition. So now that did make a very big difference whenever we were estimating. So not whenever we were taking the limit, but when we were estimating the value of our area in 5.1, of course, it made a big difference whether we chose a left endpoint or a right endpoint. So when we're estimating, when we're maybe trying to approximate the value of such a problem using a computer-based method, something that might be talked about a little bit in Calc 2, then it does matter a bit. It does matter a bit where or how you choose your index. But as far as the theoretical side of things, that if we're getting an exact answer, it doesn't matter how the xi is chosen so long as it's in that interval. Okay. And just super quick example from a previous work, just applying this notation, we can say that the integral from 0 to 4 of 4x cubed dx, that's what we found to be 4 to the fourth, or 256. That was the work that we did last time. So we're, on the basis of that support that we went through last time, we can't just say this, but because we did that last time, we're just writing this in the new notation. So not really much to this example. Any questions so far? Okay, so we have a few more theorems and properties that we're going to introduce that will help us with some of the calculations, and then we'll go through several examples. So theorem, this criterion seems a little bit sketchy. It's like, well, I mean, I don't really want to compute the limit of this sum. Like, if the limit exists and is finite, seems like a pretty big hedge there, right? Well, nicely enough, we have a theorem that says if f is continuous on a to b, then its integral exists. Now, it might not be practically all that easy for me to calculate its value, but the limit exists, this bit converges, the value of the integral exists, it's a well-defined problem. It might be hard for me to figure out what that number is, but it does exist. And in fact, so remember, continuous functions can have corners, like an absolute value or something like that, or cusps, like say absolute value of x cubed, something like that. In fact, it can even have jump discontinuities. I mean, if you really think about it, we're trying to find an area under a curve. Oh, if my function has a jump, does that really matter for the area? I mean, not so much, right? I basically just have these two areas. So a function having a jump doesn't, you know, uh, the kind of gut feeling is that shouldn't like mess up my ability to find an area under the curve. It still seems like a pretty well-defined problem. The only potential issue I have is at this one singular point, but that point kind of, this vertical line here like contributes zero area, right? Because it's a line, it has zero width. Everything else, the function is really nice. And so in fact, we are integrable if we have a jump discontinuity or finitely many jump discontinuities. And it's actually we can even extend that to countably infinitely many jumps. So like if we had a jump at every 1 over n, where n is a positive integer, and we were integrating on, say, 0 to 1. So if I'm integrating 0 to 1 and I have a jump discontinuity at 1/2, at 1/3, at 1/4, at 1/5, because I can count them, I can essentially I can say which one is the next one. If I'm standing on 1, if I'm standing at 1/3, what's the next place that a jump occurs? It would be 1/4. If I'm standing at 1/4, what's the next one? It's 1/5. So for countably infinitely many jumps, we still have an integrable function. So the integral can actually tolerate a lot of, what we think of as problems with our function. We mentioned this a little bit last time, that integration is kind of a smoothing operation. It kind of takes, it can take messy functions as inputs and turn out nicer functions. And differentiation kind of goes the opposite way, right? It gets broken pretty easily if there are any problems with the function, or it can even take a somewhat nice function and break it in a sense, can introduce a um, a corner or a jump into the derivative. So so integration actually works pretty nicely, and it can tolerate quite a lot. So some properties, these are theorems. Oh, and the reason that this is sensible, that we can avoid jumps, is we can just choose to think about this basically as two integration problems, just one to the left of the jump and one to the right of the jump. And with countably infinitely many jumps, we can just kind of take a whole bunch of little subintervals in between the jumps and, break our one big integration problem into a whole bunch of little small ones. So that's, I kind of argued it more geometrically, but that's the more maybe mathy way to think about it. So some properties, some theorems. The integral of a constant function, integral a to b c dx. Remember this dx part of the notation, I don't think I explicitly pointed this out. This dx part of the notation just tells me what variable I'm integrating with respect to. This f of x bit tells me what my function is, right? So this f of x is what I call the integrand. So for instance, down here, my function of interest, I'm having so much trouble selecting what I want to select today. There we go. I was having a lot of trouble in stats too. This is my integrand. This is the function of interest, 4x cubed. The variable of interest, the variable which I'm using to integrate over, is x. So I write a dx here. This dx is kind of a nod to the delta x here, the little change in x. Here we have a small but positive change in x, subinterval width. And here this dx we think of as an infinitesimal change in x. It's a little bit like dy dx, a little bit similar to that kind of idea, or a differential dx. And then the integral sign 0 to 4 tells me my bounds of integration. So integral to be c dx, so the function I'm integrating, if I can select it here, there we go, is just the constant function c. Well, pretty clearly this is c times b minus a. Right? I mean, we can just look at the picture. We have a rectangle, base width b minus a and height c. And its area is going to be c times b minus a. Or if we're just adding c times subinterval width to itself a bunch of times, the c basically factors out, and I just add up all my subinterval widths. Well, that's just the whole width from a to b. That's just b minus a. So this summation here, this constant factor can come out of the sum. And then when I sum up all of the delta x's, that's just the whole interval width from a to b, which is b minus a, or it's n times b minus a over n. You can think of it that way too. But b minus a times c, and all of my n's have disappeared, so the limit is just b minus a times c. So this is a pretty easy one to see in a couple of different ways. Similarly, be careful with the bounds of integration here. Integral from a to a, f of x dx. The region of integration is from a to a. So if I integrate over just a singleton, just a single number, not an actual interval, this integral is 0. Well, of course, that's because delta x has to be 0, right? B minus a, well, that's a minus a. That's just 0. we have that constants can come out of integrals. That comes from the combination of the facts that constants can come out of sums and constants can come out of limits. So the constant, if I had CF of x, comes out of the sum, it factors out, and then it comes through the limit. So it comes out of the entire integral. Integrals break up sums. Again, with the usual, stuff that provided that each of these individual integrals exist, then we can apply this. So with reasonable bounds uh, on with reasonable assumptions, I should say. And that comes from the fact that here I'm just adding a bunch of stuff up. If I add a bunch of f of xi stars plus g of xi stars, I can just take that sum, put all the f's first, put all the g's last, just using commutative properties of addition, and then collect all the f's together, collect all the g's together, and then again, if the limit of the sum is the sum of the limits as long as all of the resulting limits exist. So by the linearity of summation and of the limit operation, we get linearity of the definite integral. Super nice. That a linear combination of functions in the integrand, so integral of p f of x plus q g of x, is a linear combination of the integrals, p integral f of x plus q integral g of x. And then a little more manipulation with the bounds of integration. Integral a to b f of x dx, if I switch a and b, if I switch the roles of the upper bound of integration and lower bound of integration, what effect does that have? So how does integral a to b f of x dx relate to integral b to a f of x dx? Well, if we come back up here and we think, if I switch a and b, it doesn't affect the limit. I mean, the operation of doing the limit. It doesn't really affect the summation operation. I'm just summing up a whole bunch of boxes still. It doesn't affect the function output, the heights. But what it affects is delta x. If I swap the order of a and b minus a is negative a minus b. So if I go from b to a, I'm kind of traversing this direction. So my delta x's now are negative. My base widths are like negative numbers because I'm traversing from right to left. So everything else stayed the same except my delta x's, which are multiplied on, picked up a negative sign. And just like we said before, that negative sign is basically a negative 1 times. It just comes all the way out in front. So I can flip the bounds of integration if I tack on a negative sign out in front. This can often be a useful thing to do if, if it's a little bit annoying to evaluate from A to B, and it's easier to evaluate from B to A, you can flip the bounds to make the algebra and arithmetic easier and just pop a negative out in front. And then lastly, of course, still with the caveat that provided that all the integrals exist, integral a to b f of x dx so this signed area, if I have a number c, let's just say that it's between a and b. I can say that the signed area under f between a and b is the signed area under f between a and c plus that between c and b. I don't know why my slashes ended up so funky over there. So I can break up my interval a to b into, say, interval a to c plus interval c to b. The union of those two intervals, a to c and c to b, makes the original interval a to b. So that is quite important that the union of these two intervals, a to c, union with c to b, makes up the original a to b interval. And the integrals then can break apart that same way. This is kind of expected, I suppose. But we could even you know, let's say that 0 was a particularly nice place to start our function evaluations. I could even, consider c equals 0, integrate from a to c, and then from c to b. So c could even sit outside of the interval a to b. Again, so long as like the function is defined there, that everything, that the integral is defined and all of that. I noticed that for the part from c to a that I don't want to end up in the integral, that in part of the signed area, I traverse it once right to left. So that's with a negative sign on the delta x. And then I traverse it again left to right with a positive sign. Those are going to exactly cancel out. So I can really pick an arbitrary c as any real number, again, so long as f cooperates with it nicely and the integral cooperates with it nicely. But I can pick c between a and b, or even outside of a and b, and that's I can break my integral up that way. This is actually something uh, kind of common that we do in probability and statistics. A lot of times we are interested in finding, say, the area under a normal distribution, a distribution that we saw in optimization. And depending on what kind of normal table you have, a lot of normal tables just give you areas to the right of 0. So if I'm looking for this area here, I might choose to find that area. Let's say this is a to b. I might choose to find that area as the area between 0 and b. That includes the area that I want to keep between a and b, but it also includes some area I want to get rid of. So I subtract off the area between 0 and a. Or these are areas, that's basically just integral a to b f of x dx equals integral 0 to b f of x dx minus integral 0 to a f of x dx. And here, so I did this visually, so I intuitively see I need a minus there. But where does that minus come from? This minus can flip those bounds of integration, make a plus integral a to 0 f of x dx. Right? And there's exactly. So if you've ever taken a stats course and you've done this kind of slicing and dicing these areas with normal distributions to use your tables, you were using a lot more complicated math than you probably appreciated at the time. This is really the foundational property that says that this actually is a valid thing to do, right? When we teach stats, we just look at pictures and say it makes sense, doesn't it? But that's not real math, right? I mean, just saying, hey, this looks like it should make sense. Just because this might be how you were doing it or something, if you were cutting a sewing pattern out or whatever, that's not enough for it to be mathematically rigorous. This is the idea that really allows us to do this. Any questions so far? Okay, a couple more theorems and then, well, theorem and two corollaries, and then on to examples. Uh, the so the integral is a bit like an operator. It like takes kind of a function in and gives a number out. It takes the function in and gives the area, the signed area between that function and the x-axis on the region of interest as the output. So there's kind of the sense in which like the integral is like almost like an increasing function, how if you plug a bigger input in, you get a bigger input out, or you get a bigger output out for an increasing function. bigger input yields bigger output. There's a sense in which the integral is kind of like an increasing operation or something that in some loose sense, if you like plug in a bigger function, then you get out a bigger result. And that's what this theorem and these corollaries kind of relate to. So the underlying theorem is integral a to b f of x dx is bigger than or equal to 0 if the integrand is positive or non-negative. And of course, that makes sense. So note that here we're taking f of x bigger than or equal to 0 on a to b. So this implies that b is bigger than a. This makes sense from our definition. Delta x b minus a over n, as long as b is bigger than a, which it is because we have interval a to b, delta x is positive. And by assumption, my function output is positive. I'm adding up a bunch of positive things, product of two positives positive, adding a bunch of positive things or non-negative, and then taking a limit of those, that's going to stay positive. So I think this makes sense essentially just by looking at the definition of the definite integral. A corollary that comes directly from this is if on an interval a to b, f is bigger or equal to g, then integral f is bigger or equal to integral g. Where's the, what's the proof of this look like? We'll just take h of x equals f of x minus g of x. We've seen this kind of a strategy before a couple times now. So f minus g is bigger than or equal to 0, right? If f is bigger than g, that implies that integral a to b h of x dx bigger than or equal to 0 from our theorem. This is why this is a corollary to this theorem. It lets that theorem do the heavy lifting. And then, of course, but we have the integral of the difference, which is the difference of the integrals using the linearity of the integral. And then we just add integral g of x over to the other side and get our result. So we're just leaning heavily on this theorem, letting it do the heavy lifting here, and then just kind of moving things, to one side or the other of the inequality. And we can talk about corollary one and kind of degeneralize it in a sense. We can say if we have bounds on f, if f of x is bigger than or equal to some little m, lower bound, and less than or equal to some big M, an upper bound, on an interval a to b, then we know that integral a to b f of x dx, if we take a g to be, say, little m, is bigger than or equal to integral a to b little m dx, but little m is just a constant. So that's just little m times b minus a. That's the lower bound of the integral, and then similarly the upper bound with capital M. What's kind of the idea here? Suppose I have my function f on a to b. And if I have some lower bound, it doesn't have to be the minimum, it could be the minimum, but it's some lower bound, little m, and some upper bound, capital M. Let me actually do that in green. And I'm interested in the area between f and the x-axis. Well, I notice that little m, if I consider just the function f of x equals little m, that area is a rectangle that makes up some of the area, the black area that we're interested in, but not all of it, of course. So this is a strictly smaller amount of area than little f. And for big M, this is a larger amount of area. So big M, that function f of x, or uh, say g of x equals big M, is bigger than or equal to f of x for each x. So big M's boxes are all going to have bigger areas. The big M integral is going to have a bigger area. And its area is just going to be big M times b minus a. And little m is going to have area little m times b minus a. Those are going to be upper and lower bounds of the area related to f, or the definite integral. Any questions so far? Okay, so let's look at this example. We can try to compute integral 2 to 5 of 4 minus 2x dx. I could do this geometrically. I could evaluate this function at 2 and at 5, get signed areas. Or I could maybe use some of my properties. Just for practice, let's do it both ways. So the first is a more geometric approach. So if I plug in x equals 2, well, that gives me an output of 0. And if I plug in x equals 5, 4 minus 10 is -6. So I'm looking for this signed area. This is a triangle with height. I mean, we're going to call the height -6. It's from 0 down to -6. And with base width, 5 minus 2, or 3. So the integral 2 to 5, 4 minus x dx, or 4 minus 2x dx, is half the base times the height, -6 over 2 times 3, or that should be -9 units. We had to be careful to kind of put a negative height in here, which feels kind of strange, but that is respecting that sign. The other approach we could have taken is to use some of our properties. We could say this definite integral is the integral from 2 to 5 of 4 dx minus 2 integral 2 to 5 of x dx. Or integral from 2 to 5 of 4 dx is 4 times 5 minus 2. That was one of our properties above, integrating a constant function over an interval. Minus twice, and I need to figure out what this number is, this integral 2 to 5 of x dx. I still need to lean on geometry, but I don't have to worry so much about signs here. So I have 2 out to 5, and the line y equals x. So I have a trapezoid, and a trapezoid area is, well, what is it? It's the base width, 5 minus 2, times the average of the heights. So the height goes from 2 to 5, 5 plus 2 over 2. Or this is 4 times 3 minus 2 times 3 times 7 halves. Fingers crossed that I did all this arithmetic right. I can factor a 3 out of everything. 3 times 4 minus 2 times 7 halves is 7. 3 times -3 is -9. Was one way easier than the other? I don't think particularly, right? Part A was a little shorter, but it was theoretically more complex. I had to make sure that I had my signed area in order and all of that, right? Um, so I was able to get an answer a little more quickly. That was also mainly due to it being a triangle instead of a trapezoid, or at least partially. Up here, I leaned more on my algebraic properties. So the kind of strategy was a little more straightforward. I can more just like follow my nose. But the arithmetic was a little more complicated. I don't know, it's a trade-off. But we got the same answer either way. We could use our more algebraic properties or lean a little more heavily on the geometry for this problem. Any questions on that? All right, let's look at something like this. Integral 0 to 3 of 1 plus root 9 minus x squared dx. Now this one actually could be pretty tough, right? I mean, if I consider this function, that's not really a function I'm familiar with. I might notice that I just have integral 0 to 3 of 1 dx plus integral 0 to 3 root 9 minus x squared dx. I can apply a property, and I know this integral is easy to do. So what about this one? I might actually recognize root 9 minus x squared as a part of a circle. Right. So I probably should recognize this at this point as the top half of a circle of radius 3. And also, nicely enough, my interval of integration goes from 0 to 3, goes along the whole radius of that circle. So let's take a look just at this integral. So I have this quarter circle of radius 3. Well, the area of a circle of radius 3, pi r squared, is going to be 9 pi. That's for the whole circle, but I have a quarter circle, so it's 9 pi over 4. So I have plus 9 pi over 4. And then, of course, this integral is easy to do. We're going from 0 to 3 on the x-axis and just height 1, constant height 1. That's 1 times 3 minus 0, or just 3. So by using an algebraic property to break up our integral, that kind of made the geometric property, or the geometric side of things, a little more obvious, a little more evident, and easier to deal with. So we're meshing the algebraic structures and geometric structures. I think there's a lot of power to that. Either being able to like get intuition from one side and solve the problem on the other side, or solve the problem on one side and use the other, geometry, algebra to kind of check your answer for reasonability, or something like this, that just we applied an algebraic property, and that made the geometry kind of stick out to us a little better, so we switched gears to geometry. Any questions so far? As an exercise, try to compute this. Integral 0 to 1 over root 2 of square root of 1 minus x squared dx. This actually is not a nice, say, like quarter circle. It's something like this. And the hint that I gave you here is consider this as a circular segment. This is a portion of a circle plus a triangle. So here we have a triangle. We know how to deal with triangles from geometry. Here we have a circular segment. We can treat that similarly to how we treated this one up here. So, and then add those two together. And the answer should be 2 plus pi all divided by 8, or 1/4 plus pi over 8. Okay, so another example. So if I just asked you what is integral 0 to 4 of 4x cubed dx, we really can't do that quickly. Pretty much still the only way that we have to approach this problem is to do it kind of the way that we did it in section 1 with upper and lower bounds, or maybe we can uh, all the way back up here, there we go. Maybe we can directly apply the theorem here, or sorry, the definition along with, well, this note here, this note. It's the one I was looking at. So it turns out that, say, for instance, choosing the left endpoint in each subinterval, which is what gave us a lower bound, that's equivalent to just computing this limit anyway, or choosing the right endpoint, which gave us the upper bound, is equivalent to just computing this limit anyway. So we really don't need to use the squeeze theorem. We can lean on this theorem, even though, like I said, it's unproved. At this point, it's more of a subject for another course. But it's not like we could either rewrite this somehow in a nice geometric way, or even that we could do much algebra with it. I mean, I suppose we could pop that factor of 4 out front, but still integral 0 to 4 of x cubed dx, that didn't really help us all that much. However, if we did the work to get this, we might be able to leverage that information down here. I would like to compute integral 0 to 4 of 3 minus 12x cubed given this information. Can I leverage that? Well, sure, this is integral 0 to 4 of 3 dx minus, well, 12x cubed looks like 3 times 4x cubed. I'll pull that 3 out. And here I have 4 minus 0, or just 4, times 3. That's 12 minus 3 times, and this bit, I've used my algebraic properties to massage the difficult part so that it looks like something that I already know the answer to. I've reduced my problem to a previously solved problem. That's something that we like to do in math. I say, hey, I cordoned off my difficult part and made it look like something that I've already done the hard work to solve. And now I can just put in the answer, 256, and whatever that turns out to be. So we had a small, in some sense, small change to the integrand. We could use our previous integral to find that solution. If I have a small change to the region of integration, can I do the same? Not so easily, right? Unless I can find something really special about, like, say, integral 0 to 1 and integral 2 to 4, then maybe I could break those pieces off or something and like solve for the integral of interest in terms of these ones and the one I already know or something like that. But that doesn't seem like it's going to work. The answer here is no. By changing the region of integration, we've really fundamentally changed. We've really fundamentally moved away uh, from this integral up here. So we probably would have to go back and just redo our section 5.1 work on this new interval 1 to 2. Any questions on any of this? All right. And then let's use corollary 2 to estimate integral 0 to 1 of e to the x dx. So again, this is a function e to the x that's not going to work super nice geometrically. It's not like a portion of a circle or something, certainly not a flat line, not a straight line or anything like that. But maybe we can estimate its value. Let's jump up here to corollary 2 and copy it down. So on the interval 0 to 1, can I find a lower bound and an upper bound for e to the x? And if I'm going to find a lower and an upper bound, I might as well make them pretty tight bounds, right? Can I find a minimum and a maximum on the interval 0 to 1? I know e to the 0 is 1. 2.7 or so. Here's 1 comma e and 0 comma 1. So I'm looking for this area. I know that e to the x is an increasing function. The larger the input, the larger the output, right? Its derivative is e to the x, and e to the x is always a positive number. So I know that the minimum on 0 to 1 is at 0, and it has value e to the 0 or 1. So I choose little m equals 1. That is a lower bound, and in fact, it's the greatest lower bound. It's the minimum. I couldn't choose any other bound that's higher than that and would still be a lower bound. And similarly, the max is going to be at 1 at the right endpoint because it's an increasing function. And its value is going to be e to the 1 or e. So I choose big M, the upper bound to be e. My function is always going to be less than e, less than or equal to e on this interval. And this is a least upper bound. If I tried to pick an upper bound that was below e, I wouldn't be able to find such an upper bound. So I know that, try to keep my color coding going here. I know that integral 0 to 1 e to the x dx. I know that it is bigger than or equal to little m, 1 times 1 minus 0, b minus a. And I know it is less than or equal to big M, or e, times b minus a, 1 minus 0. Or this integral, it has a value between 1 and e. So somewhere between 1 and about 2.7 or so. Right, so it's not a super tight bound. I don't have like 3 decimal places of accuracy or something, but I also didn't really have to do much work to get it, right? Any questions on 5.2 on the definite integral? Okay, let's start on 5.3 then, the fundamental theorem of calculus. So we're going to start right off with the actual theorem, the fundamental theorem of calculus. Each of the, maybe not everyone, but most of the big areas of math have like a fundamental theorem of something. So like the fundamental theorem of algebra is that nth degree polynomials have exactly n roots, counting multiplicity in the complex plane. So the fundamental theorem of calculus, it's a pretty important theorem in calculus. So let's see what it says. It has 2 parts with one assumption. The assumption is that f is continuous on closed AB. I mean, that's obviously going to make all of our integration stuff nice because we had a theorem that said that integrals of continuous functions exist. We don't know if, if we just had an arbitrary function, we wouldn't even know if its integral existed or not. So our assumption, f is continuous in AB. Then we have 2 conclusions. There's part 1 and part 2. I split them up funny like this because if I put them on the same line, the integral symbols just don't look nearly as nice. They're harder to read. So, okay, so don't need that extra space. So fundamental theory of calculus part one, which kind of ironically is the less maybe important or less often used of the two, says that this function defined by little g of x equals integral from a to x f of t dt. Well, let's take a second and ask ourselves, what the heck does this even mean? So let's come over here and look at g of x equals integral a to x f of t dt. So here I have a function f on some interval a to b. I have some value x that's between a and b. And for a given choice of x, I have a certain area. So if I come down here and look at g as a function of x, well, when x equals a, then I'm integrating from a to a f of t dt. G has to be 0 there. When x is a little bit to the right of a, the integral is going to be a little bit positive. When x is a little more to the right of a, the integral is going to be a little more positive. There's a little more area there. Let's actually make a slightly more interesting function f. Kind of drew my standard boring function. When x is even a little more to the right of a, note that we are still accumulating positive area. We're accumulating it less fast, though. So we're still increasing, but we're flattening off. So we start by increasing pretty quickly, then a little less quickly, and then we are still increasing, but we're flattening off. Once we get to here, where f changes from positive to negative, well, now when I go a little bit further, I get a bit of negative area. Now note, g does not turn negative at this point, because I still got a lot of positive area built up. So I got a big positive number minus a small negative number. We just come down a little bit. We add some more negative area in, we come down a little more. Add some more negative in, increment a little more negative, we come down a bit more. Maybe after a while, we get back down to where we're, say, a little bit negative. So g might look, something like this. Or a function f that looks like that. So this would be like the t-axis. It's kind of bad form to use the same letter to mean two different things. So that's why we're just calling it integral a to x f of t dt. So we're very clear that these correspond to the same variable and these correspond to the same variable, but those aren't the same variable between the x's and the t's. If I made it integral a to x f of x dx, then it's like, well, now we have the same letter kind of meaning two different things. So that's what we mean here. So g of x, integral a to x f of t dt. So if f is continuous on closed AB, then g is also continuous on closed AB. So if I plug a continuous function in and integrate it, I get essentially something like a continuous function out. It's differentiable on open AB. And furthermore, its derivative is g prime of x equals f of x. So we're evaluating f at this variable endpoint. And fundamental theorem of calc part 2 says integral a to b little f of x dx, the definite integral that we might want to compute for a certain function on a certain interval. And this is kind of the magical part, the practically powerful part of fundamental theorem of calculus. This is big F at b minus big F at a. Our integral we can turn into a function evaluation. How? By choosing a function that is the antiderivative of the integrand. So a few notes on this. Note 1, the first part of the fundamental theorem of calc says that if I differentiate this thing with respect to x, in other words, if I take d by dx of integral a to x f of t dt, I get f of x back. So kind of if I take the derivative of an integral in a specific way, I get the integrand back. And 2 says that if I integrate a derivative, right, big F is an antiderivative of little f, which means big F prime equals little f. It means I can plug big F prime in here for little f. Integral a to b of big F prime of x dx equals like little f evaluated from a to b. This notation means evaluate big F at b, subtract off the evaluation of big F at a. So that's what this notation here means. Or in a sense, if I integrate the derivative, I get something that looks like the original function back. If I differentiate the integral, I get something that looks like the original function back. There's a sense in which integration and differentiation act kind of like inverse operations of one another. They're not, exactly inverse operations, but there's a sense in which they are. Second note, this general idea of fundamental theory of calculus, basically what it says is that integrating a derivative over a region, integrating a derivative of a function over a region, over an interval, in this case, a one-dimensional region, is equal to or equivalent to evaluating the function at the boundary. So evaluating the function whose derivative I took at a boundary. The boundary of this interval from a to b is the endpoints a and b. This general idea is extremely generalizable. I guess I said that a funny way. The general idea is generalizable, but for instance, if we, were to look ahead to calculus 3, we would see the fundamental theorem of line integrals looks very much like fundamental theorem of calculus. Green's theorem, Stokes' theorem, and the divergence theorem look very different at their surface level, but they're all generalizations of fundamental theorem of calculus. They say that doing something over a region, maybe a two-dimensional region or maybe a three-dimensional volume, adding up something over a 2D region or a 3D volume that has to do with derivatives, instead of doing that, we can evaluate along the surface, maybe the surface of a two-dimensional region or the boundary of a two-dimensional region is a curve in that two-dimensional space, or the boundary of a three-dimensional volume is a surface embedded in a three-dimensional space. So these are all generalizations of fundamental theorem of calculus. So you can see that this is really laying some like bedrock foundation that a lot of important ideas are going to build on. You can tell when you have so many things that are named after people. I think the divergence theorem has another name that's like Cauchy's theorem or Gauss's theorem or something like that. But when there are so many theorems that are named after people that are like directly based on this idea, that kind of suggests that it's really, well, fundamental, I suppose, fundamental theorem of calculus. And then I've already pointed this out, but note the practical relevance of part 2 of the fundamental theorem of calculus, that instead of doing, right, up until this point, the only way we could compute a definite integral was, one, to interpret geometrically, and that solved a very limited number of integrands, or two, to try to do this summation and hope that the integrand is simple enough that I can actually rewrite the summation in terms of something nice, like maybe n times n plus 1 over 2 or something like that, and then take a limit. Again, the chances of that happening, not so great. So at best, it's a ton of work. If you remember from 5.1, that was a lot of work for a comparatively simple problem, just a power function. But we've reduced the problem to simply finding an antiderivative. If we can find an antiderivative of the integrand, we can just evaluate it, right? That's all that this is saying, is just evaluate this function at two inputs, and we have our answer. Now, that being said, saying just find an antiderivative, well, for some integrands, the antiderivative is easy to find. For some, it's moderately difficult, and for some, it's extremely difficult or impossible. So, this just, I suppose, should be taken with a bit of a grain of salt. But I think that I think that even for the problems where finding the antiderivative is quite difficult, going with the original definition would be intractable or impossible, one of the two. Okay. So for example, I mean, we took, I don't know, half an hour or something to come up with this statement here and give a good argument behind it. And that was only, say, half-ish of the problem. It left the other side of the problem for you to do. But even after the definition of the definite integral and the basically theorem that says it doesn't matter where we pick xi star, if one of them converges, they all will. Okay, so then maybe we only needed to do what we called un previously, or we only needed to maybe do ln previously. We needed to do one of them and didn't need to use the squeeze theorem, although we chose to at that point. Well, now we can do this almost trivially. So f of x equals, let's leave the 4 in there, 4x cubed. Big F of x is x to the fourth. I might put a plus c on here, but one little note here is big F can be any antiderivative of little f. Why is that? Well, if I get big F of b plus c minus big F at a plus c, the c's just go away. The plus c's don't actually stick around. They just subtract off. So typically when I'm looking to solve a definite integral like this, I'll choose to work with the simplest antiderivative, typically the one where c equals 0. F prime of x is 4x cubed. That is little f. That looks good. So I can say that integral 0 to 4 of 4x cubed dx is big F at 4 minus big F at 0, or that's 4 to the fourth minus 0 is 256. Okay. We can do in, a minute, including me explaining all of the steps and talking about all of this, what it took us maybe a half an hour or something to do before. So, obviously a very powerful practical tool, in addition to being an important theoretical idea, right? In addition to kind of laying a lot of the groundwork for a lot of future ideas and big theorems, it's also just a very nice practical tool. We can now compute integrals fairly straightforwardly. We at least have a pretty decent plan of attack. If I wanted to compute integral 0 to 4 of 3 minus 12x cubed dx, I might not even go through the trouble of using my properties here. I might just look for an antiderivative of this. That's going to be something like 3x. That differentiates the 3 minus 3x to the fourth. That differentiates. The 4 comes down, makes a minus 12. And take one off the power, x cubed. That looks good. I'll just evaluate that from 0 to 4. I see when I plug in 4, I get 3 times 4 minus 3 times 4 to the fourth. Subtract off evaluating this at 0. 3 times 0 minus 3 times 0 to the fourth. Well, that's all 0. Or this gives me what? 12 times 1 minus 4 cubed, whatever that ends up being. So in this case, I didn't even apply the properties because I didn't really even need to. I could have if I wanted to, but I didn't really need to. If we look at something like integral 2 to 5 of 4 minus 2x dx, so here's my little f of x. What's big f of x, the antiderivative, I can antidifferentiate each term separately. This gives me 4x minus x squared. Let's see, I differentiate the first term, I get a 4. Differentiate the second term, I get a minus 2x. That looks good. Then this is going to be f of 5 minus f of 2. F of 5 is going to be 4 times 5 minus 5 squared. Subtract 4 times 2 minus 2 squared. 20 minus 25, that's minus 5. Subtract 8 minus 4 is 4, negative 9. I think even with a pretty simple geometry problem, remember this was the same one that had that like triangle below the x-axis, that was this one, or that we used the properties on this same problem, we got negative 9 up here. I think even with it being a very simple geometry problem, it was actually quicker to do the fundamental theorem of calculus bit than to do all of that up there. All right, next example. Let's try to compute this using the fundamental theorem of calculus. Integral 0 to 3 of square root of 9 minus x squared. We did this as a, well, I guess as a part of a bigger problem, but it was a quarter of a circle. This one, though, I don't know. I mean, I might be tempted to do something algebraically, like make this 3 minus x or something like that, but I know, of course, that's not right. So I don't want to get too fast and loose with my algebra here. Is there any function that I know that has a derivative that's square root of 9 minus x squared? I might try something like 9 minus x squared to the 3 halves, thinking that if I differentiate, the 3 halves bumps down to a 1 half. But the problem is the chain rule pops out a factor of 2x, and I don't have an x out here to kind of help with that. So kind of in short, this one's a lot easier to do with geometry. I recognize it as part of a circle. I can go that route. Finding a function whose derivative is root 9 minus x squared isn't all that easy. It's not impossible, but that's what a decent bit of the beginning of Calculus 2 is about, is looking at some tools and techniques to help us find antiderivatives for functions where maybe the antiderivative isn't so obvious. So we can do it for this one, but it's a little more of a challenge. It's not so easy as just looking at it, writing down the antiderivative, and writing down the answer. For this one, at this point, the best approach would be the geometry approach, seeing that it's a quarter circle and using the area of a circle. What if we have something like this, integral of negative 2 to 2 absolute x dx? I know that this shouldn't be a problem because integrals can handle things like corners and even jump discontinuities just fine. or because if I look at these two areas, I mean, this seems to be a perfectly reasonably well-defined problem. Just the areas of two triangles. Well, I see that this has base width of 2 times height of 2. And the same triangle on the left, this is just going to be 4 by geometry. Now, if I wanted to, I could do this a little bit of a slicker way. I could, maybe use fundamental theorem of calculus and all this, but it was very quick to do this with geometry, right? I probably would just do the geometry here because it's so quick and easy. But I could say, well, this is when absolute value of x, I know that that is a piecewise function that splits at 0. So this is going to be the integral from -2 to 0 absolute x dx plus integral 0 to 2 absolute x dx. But on my first integral, my inputs from -2 up to 0 are all negative. In that case, absolute value of x is just -x. If I have a negative input, I put another negative in front of it to get rid of the negative and make it positive, right? And on 0 to 2, on that interval from 0 to 2, my inputs are always positive. In that case, absolute x is just x. Or I see that this is -1/2 x squared, right? That's the antiderivative of -x, evaluated from -2 to 0, plus 1/2 x squared, evaluated from 0 to 2. This first one gives me 0. When I plug in x equals 0, I get 0 out, minus this stuff evaluated at -2. So minus a -1/2 is plus 1/2 times -2 squared, plus this evaluated at +2, 1/2 times 2 squared, minus this stuff evaluated at 0, which is just 0. I get 1/2 times 4 plus 1/2 times 4 is 4. That was a heck of a lot of work for what I got in 10 seconds by just looking at the geometry, right? Just because I can force the use of an algebraic method, I can break this into two integrals using a property. I can get rid of the absolute values that way. I can use fundamental theorem of calculus a couple of times. I mean, that uses a lot of cool stuff, but right, I could get the answer in, 1/10 of the time going the geometric route. So just because fundamental theorem of calculus is available doesn't mean that it's always going to come in and save the day. Sometimes there's a better method, but often fundamental theorem of calculus is going to be by far the best method. So, I mean, obviously I'm choosing problems to illustrate certain points here. So don't think that, half of the integrals that you do from now to the rest of your, engineering career are going to be geometrically based. They're not. They're mostly going to be fundamental theorem of calculus, but just illustrating the point that, just because you can use fundamental theorem of calculus doesn't mean it's always the easiest approach. Okay, and maybe let's actually skip this example. Let me change the order here. We'll leave that example to next time because I don't think we'll hit both of these in 9 minutes. But let's take a look at this one. Compute integral 0 to pi of secant squared of x dx. Seems like there's an extra space in there. There it is. Okay. Integral 0 to pi of secant squared x dx. And I look at this and I actually notice, well, nicely enough, I have an antiderivative for secant squared. Whose derivative is secant squared? I think that's the derivative of tangent, right? Derivative of tangent is secant squared. So if this is little f of x, big F of x is tan x. Again, if we wanted the most general antiderivative, we do tan x plus c. But for the purposes of fundamental theorem of calculus, we only need an antiderivative. We'll pick the simplest one. So this is tan pi minus tan 0. Tangent is sine over cosine. Tan pi is 0. Minus 0 is 0. Well, now that's kind of an interesting result, right? We integrated secant squared x, clearly a non-negative function, because it's something squared, right? It can't be negative. We integrated it over a non-trivial interval. It's not an interval from like 0 to 0 or something like that. So I integrated a function that's greater than or equal to 0, and certainly for sometimes is strictly greater than 0. There's certainly going to be some intervals. I mean, secant squared x isn't just the 0 function. Sometimes it's going to be strictly bigger than 0 on an interval from 0 to pi. I'm adding up a bunch of stuff. Maybe every once in a while the stuff is 0, but sometimes it's positive. It's never negative. How do I add up a bunch of stuff that's positive, not add anything negative to it, and get 0? Right? This integral clearly should be bigger than 0, but we said that it's equal to 0. What's the problem here? Well, wait, secant squared x, that's 1 over cos squared x. So what is secant squared of pi over 2? It's undefined. It's not undefined as, just a jump discontinuity or something like that, or a corner. It shoots off to infinity, right? We're getting a 1 over 0 type situation here. So secant is going to kind of look something like this there. And, so, I mean, what do we get out of this? Does the fundamental theorem of calculus not work or what? Well, remember, it's really easy to forget when we get so in tune with just the process of get the antiderivative, evaluate, and you're done. We have an important assumption here. We should be checking every time, is f continuous on AB? Is this continuous on 0, 4? Yeah, it's a power function, no problem. What about this one? Yeah, no problem. Polynomial. Polynomial, continuous. This thing on 0 to 3, I mean, it's not continuous on 0 to 4, because 9 minus x squared under the radical, but on 0 to 3, no problem. Is absolute x continuous? Yes. Differentiable? No, but continuous? Yes. Is secant squared x continuous on 0 to pi? No, it's not. None of this is valid at all. I mean, this is what evaluating the antiderivative would give you, but that's not the value of the integral because fundamental theorem of calculus doesn't apply. So integral 0 to pi, secant squared x dx. We don't know what to do with that. We can't apply fundamental theorem of calculus. We know that much. Discussions of what to do when things shoot off to infinity under the integral sign. That's something that's a Calc 2 topic, improper integrals. So that's beyond the scope of this course. But that's something we'd investigate in Calc 2, looking at these improper integrals when we have something shooting off to infinity, either vertically or horizontally, and basically how do we handle that? But for this one, just a cautionary tale. We can't do any of this stuff with trying to apply fundamental theorem of calculus. We can't apply the conclusion because not continuous on 0 to pi. Now, importantly, if we had, I don't know, 0 to pi over 4 or something, well, then we could have done all that. We could have done exactly what we did before, just with pi over 4 instead of pi, and we'd have gotten an answer, and we'd have got tan of pi over 4 as some positive number, and that would have made sense, and it would have been right, because we would be continuous on, say, 0 to pi over 4, but not on 0 to pi. Any questions on anything from today?